Today, we're going to work on finding some partial derivatives. Yesterday, we talked about a function of two variables and how it will have two partial derivatives. So if z is a function of x and y, then we'll have a partial derivative of z with respect to x and a partial derivative of z with respect to y. And we have to have notation for both of these because this is a math class. And we have to have notation for everything. And just like with derivatives of a single variable, we're going to have two different styles of notation, a Newton style notation and a Leibniz style notation. So we have the partial derivative of z with respect to x. We can write this as dz dx. So that'll be the partial derivative of z with respect to x. We still say dz dx. I don't think I could at this point train myself to say something else, but we don't write just a regular old d. We write these weird looking upside down and reversed nines for the d for partial derivatives. We also have a variation of prime notation where we just use a subscript with the variable that we're taking the derivative with respect to. So we'll have fx at xy. If we don't have a variable z, we could just say the partial derivative of f with respect to x. So we can also list df dx. So here we have the partial derivative of z, partial derivative of z with respect to x. But there are two variables, so we will also have a partial derivative of z with respect to y. So we'll say partial derivative of z with respect to y. Where we would write dz dy, or in a Newton style notation, we'll write fy at xy. And we could also say the partial derivative or partial derivative of f with respect to y. We could put the name of the function as the thing that we're taking the derivative of. All right. The big idea is the same that we were using yesterday. If we want to look at the rate of change of z with respect to x, we just hold y constant. If we want the rate of change of z with respect to y, we just hold x constant. So to find fx at xy, we consider y to be constant. And to find fy at xy, we just hold x constant. So to find fx, we're going to treat y as constant, and to find fy, we will treat x as constant. So let's look at an example. Let's suppose that we have f of xy is equal to 2 x to the third, y to the fifth. And we want to find both partial derivatives. So to find fx at xy, we just think of the y to the fifth as being a constant. Just treat it like a constant. And in this case, y to the fifth is a constant multiple. So fx at xy we'll take the derivative with respect to x. The derivative of 2x cubed is 6x squared. And we just keep the y to the fifth. We are treating the y to the fifth as a constant multiple, and it just gets carried along. So we treat y to the fifth we're treating the y to the fifth as a constant multiple, just like we did with the 2. We'll do the same thing if we want the derivative with respect to y. I've probably just kept all my constants together, but if with fy at xy, the derivative of 2x cubed y to the fifth with respect to y, the 2x cubed is all constant. So 2x cubed, we think of that as being constant, and we multiply by the derivative of y to the fifth times 5y to the fourth. So we end up with 10x cubed y to the fourth. In this case, x cubed is a constant multiple. In the y direction, x is not variable. There's 2 partial derivatives because we have a function of 2 variables. So we can see how the function is changing in 2 different directions. So we don't want to say find the partial derivative. That doesn't make any sense. There needs to be more because they're partial derivatives. The important thing now is what this is going to turn into is a reading exercise. We're going to have to be able to read what's going on in a function and separate out what's constant and what's not constant. So if I look at another function, say g of xy, let's suppose g of xy is x to the fourth plus y to the fifth. And we want to find the 2 partial derivatives. In this case, when we find gx at xy, the partial derivative of g with respect to x, y to the fifth is considered, the y is considered constant. So the y to the fifth in that case is a constant term. So here, if we take the partial derivative of g with respect to x, the derivative of x to the fourth is 4x to the third. And the derivative of y to the fifth as a term is 0. So in this case, y to the fifth is a constant term. And the derivative of a constant term is 0. So similarly, the partial derivative of g with respect to y the derivative of x to the fourth, a constant term, is 0. And the derivative of y to the fifth is 5y to the fourth. So x to the fourth is a constant term. And the derivative of a constant term is 0. Keep in mind, we're not doing anything new. We're not doing anything new. In the previous problem, it would be like taking the derivative of 7x to the third, and you'd have 21x squared. In the second problem, it would look like 7 plus x to the third, and the derivative would just be 3x squared. So we're not doing anything new. We just have to remember some extra stuff. For the partial derivative with respect to x, the y is just a constant. Constant multiples just tag along. The derivative of a constant term is 0. Any questions? Once we get used to reading these expressions, all we have to do is incorporate all the other derivative rules that we have. Product rule, quotient rule, chain rule. So for example, let's suppose that z is equal to x to the fourth plus y to the fifth to the third. Here I have a function inside of another function. I've got an x to the fourth, y to the plus y to the fifth inside a cube. So we're going to have to use the chain rule. So the partial derivative of z with respect to x we take the derivative of the outside with respect to the inside. So we'll have 3 times x to the fourth plus y to the fifth squared. And then we'll multiply by the derivative of the inside, which is 4x to the third with respect to x. This would be a very weird way to write it. We should probably clean this up and write, I don't know why I picked red for my partials with respect to x. I'm gonna have to change that because this is looking very harsh. This would be a better way to write this function, except for the red ink part. So we wouldn't want to use x and y. In this case, z is a function of x and a function of x and y. So there's a partial derivative with respect to x, and then a partial derivative with respect to y. There's two separate derivatives. So the partial derivative of z with respect to y, we'll take the derivative of the outside with respect to the inside. So 3 x to the fourth plus y to the fifth squared. But the derivative of the inside in this case is with respect to y, so 5y to the fourth, which we would probably simplify as 15y to the fourth times x to the fourth plus y to the fifth squared. So for a function of two variables, there's always going to be two partial derivatives. Like the Sith in terms of the fact that there's always going to be two, but unlike the Sith, it's not always a master and apprentice. This is just a skill that we need to acquire. Not because later on in your future career as a fill in the blank, you're going to be finding partial derivatives. Most likely, if you're in some job where there's technical stuff going on, if you start using the chain rule to find the derivative of a function that you're working with by hand, you're probably about to get fired. So that's not a thing that's going to happen. But that's not the point of the skills. Let's look at another example. Let's suppose that P of xy is equal to sine of 2x cubed y to the fifth. In the previous example, x to the fourth and y to the fifth were in separate terms. In this example, the x to the third and y to the fifth are factors. So when we take the derivative of the inside, we're not going to be taking the derivative of a constant term. We'll be taking the derivative with a constant factor. So let's find our two derivatives. So px at xy. The derivative of sine of a thing is the cosine of that thing. Times the derivative of the thing. In this case, I want the derivative with respect to x, which is 6x squared y to the fifth. Just using the chain rule. The derivative of sine of thing is cosine of that thing times the derivative of the thing. The derivative with respect to y, the derivative of sine of thing is cosine of thing times the derivative of the thing. In this case, we're taking the derivative with respect to y. 2x cubed is constant. So I'll have 2 times 5 is 10, x cubed, that's all constant, y to the fourth.
How come in this case we didn't turn the constants into zeros?
The constants in this case were constant factors, not constant terms. The derivative of a constant term is 0. The derivative of a constant factor, or the constant factors, just follow along in the derivatives.
Okay, I see.
It's the difference between, if we drop it back to the single variable case, imagine the function sine of x cubed plus 2 versus sine of 2x cubed. In the first one, the 2 is a constant factor. In the second one, 2 is, in the first one, the 2 is a constant term. In the second one, the 2 is a constant factor. Math is just a reading exercise. We've got to take all these symbols and learn what they say. And then we start doing stuff to them. So that's what makes it complicated. Because it's really hard to read. Yes.
For the previous example, is there any way that we can write, use another notation like the px, xy for the z? Or can we say zx, xy?
No, in this case, z is another variable. So this function doesn't have, I don't have a name for this function. So the px and py notation, that's when we have a named function. In this case, since I just used the variable z, I didn't name it z of xy. That's why I used the Leibniz notation here.
Got it, thank you.
If you put zx at xy, everybody would know exactly what you're talking about. But I usually reserve px and py. I usually reserve that for names of functions. Even though we use y prime all the time for dy dx when y is a function of x. Any other questions?
So for the second example, would we be able to use the Leibniz notation for that one?
Sure, we could say partial of p with respect to x. Or the partial of p with respect to y.
Yep, thank you.
My partial derivative d's are already getting sloppy, so. Any other questions? Other than this, it really just comes down to reading our function and remembering our derivative rules. So we want to read a function and remember derivative rules. So let's take a look at, let's come up with another example. Let's suppose that we have a function, let's say q of xy is e to the x squared times y times the sine of x cubed. So when we look at this function, I've got e to the x squared y and sine times sine of x cubed. So I have the product of two functions of x. So when I find qx of xy, I'm going to have to use the product rule. So let's write down, so qx, oops, there we go. Qx of xy, we're going to have to use the product rule because I have a product of two functions of x. So notice over here, I have one function of x times another function of x. because all the rules for derivatives still apply. This is the great thing about derivatives. Once you learn product rule, quotient rule, chain rule, you are done with your derivative taking rules. There's nothing, there's no function that we can create that you can't differentiate. As long as it's differentiable. Looking at you, Weierstrass. So we're going to use the product rule because I have a function of x multiplied by another function of x. So we'll take the derivative of the first. The derivative of e to the something is e to that thing times the derivative of that thing. So there's the derivative of the first times the second. Plus the first times the derivative of the second. The derivative of sine of a thing is cosine of the thing times the derivative of the thing so we had to use the product rule. Derivative of the first times the second plus the first times the derivative of the second. I'm not sure how you remember your product rule, but we did f prime g plus f g prime. I know some of you probably learned your product rule as f prime g plus g prime f, and I just think that's weird. There should be a y in the first term. The derivative of e to the x squared y is e to the x squared y times the derivative of 2xy. So yeah, there should have been a y with the 2x. So we want to also find the other partial derivative, qy at xy. And in this case, we do not need to use the product rule. When we look at this function, we see a function of x times another function of x, and that tells us to use the product rule. Sometimes I even remember to use the product rule properly. But when we look at it for functions of y, we see a function of y and a constant factor. Sine of x cubed does not have any y in it, so sine of x cubed is a constant factor. We don't need the product rule for qy. Sine of x cubed is constant with respect to y. We would not be wrong if we used the product rule, but we would have to write the derivative of sine of x cubed with respect to y. That's going to be 0. So one of these terms is just going to drop out. So to find qy of xy, we're just taking the derivative of e to the x squared y. The derivative of e to the x squared y is e to the x squared y times the derivative of x squared y with respect to y. In this case, y is to the first power, so we're just left with x squared. Sine of x cubed is all constant factor. Sine of x cubed is constant because there's no y in it. As far as y is concerned, this is e to the x squared y times 5. If you took the derivative of sine of x cubed with respect to y, the derivative of sine of something is cosine of that thing times the derivative of the thing. So we would write cosine of x cubed times 0. because the derivative of x cubed with respect to y is 0. And that's why that second term would drop out. We don't need to write fg prime. Any questions? I don't know what you mean by did I repeat constant 2 times? So I didn't write partial z with respect. I didn't write dz dy because I technically don't have a z running around this problem. So sine of x cubed is constant with respect to y. The derivative, we're just using the qx and qy notation for the derivatives. So here's the derivative. If z equals q of xy, I could have written this as dz dy. But since I didn't have a z, I didn't write dz dy. I could have written dq dy. Yeah, you can say dq dx or dq dy. All right, let's look at one more example. So that is correct. So the question is, if we had a sine of x times y, that would not be constant with respect to y, because we would have another function of y. So if, let's say we had z is e to the x squared times y times sine of x cubed y. Now I have product rule for both. I have a function of x times another function of x. I have a function of y times another function of y. So this would be product rule for both. Other than this technical thing that we have to get used to, this skill that we have to build up, the way we interpret these derivatives is the same as the way we interpreted derivatives before. So for example, if I have a function of 2 variables, let's say v is equal to 1/3 pi times r squared times h. So this is the volume of a cone with a base radius of r and a height of h. We'll have 2 derivatives, dv dr and dv dh. So dv dr we'll just take the derivative with respect to r. H is a constant multiple, pi is a constant, 1/3 is a constant. So I'll just take the derivative of r squared, which is 2r. So the 1/3 pi and h is all constants, and the derivative of r squared is 2r. And we will write this as 2/3 pi r h. This will tell us how the volume is changing with respect to the radius. Rate of. So this is what we would use if we want to see how changing the radius would affect the volume. When the radius increases by 1, the volume will increase by 2/3 pi RH. We can also find dVdr. How does the height affect the volume? So dVdr, dVdh. So 1/3 pi and r squared, all that is constant with respect to h. And then the derivative of h is just 1. And this would be the rate of change of the volume with respect to the heights. So if the height increases by 1, the volume will increase by 1/3 pi r squared. So this is, we write the same thing for partial derivatives, same interpretations for partial derivatives that we would for derivatives of a single variable. We don't want to use regular derivatives because the rate of change has to be measured with respect to something. Your speed is only a rate of change, is not just a rate of change of your position, it's how your position is changing with respect to time. So we can't use regular derivatives because we don't have functions of one variable. We have two different inputs for these functions. If we think back to the example we had yesterday, where survivability was a function of time and concentration. If you said find the derivative, that doesn't mean anything in that context. The derivative because it raises the question, the derivative with respect to what variable? How is survivability affected by time? How is survivability affected by concentration? There are two variables that we're putting in. We can't just say the derivative because we have a function of two variables. So it's not a choice between regular derivatives or partial derivatives. That's determined by the function that we're looking at. Got a function of two variables, we have to use partial derivatives. We only have partial derivatives available. There are no regular derivatives here. Any other questions? Comments? All right. In that case, that's going to do it for today. I have to change I just noticed there's limited attempts on homework 14.1. So I have to change that to unlimited attempts. I think I can change that. If I don't change the problems, I think I could change that without changing your scores. So Let's see, more homework will show up. It'll be about taking derivatives. And let's see, I think that's it. There will be more quizzes before we have a test. And in any case, the tests will just show up online, just like the quizzes and just like the homework, you'll have unlimited attempts. So, any questions, comments? Snide remark. We're not going to have a test. We're not going to have exams where everybody stops and has to show up at the same time and take the exam at the same time. I don't want to have synchronous exams. This is an asynchronous class, so I'm not going to have synchronous exams. I think tests are BS anyway, the way that we use them. I think the way that we test is dumb. It doesn't encourage you to learn. It encourages you to compete. The final will be multiple attempts, but you'll have a more shorter amount of time. Any other questions? I know you've all been conditioned to primarily concern yourself with tests. And I know I kind of treat tests as a dumb artifact of the way that we used to, that we think we want to teach people. But I have many reasons, and I will go on at length about how tests and how we use them are dumb. I find them counterproductive to actually like learning things. I don't even want to don't get me started on the ACT and the SAT. The SAT is very good at measuring how good you are at taking standardized tests. That's what it says. That's what it measures. Some of you are going to have to take the graduate record exam, which measures how good you are at taking standardized tests. Now, it may sound like I'm really bitter about these tests because I did poorly. I did awesome on the SAT and the GRE because I'm really good at standardized tests. I don't know why. I think it's because I understand kind of how they work and I figured that out. But I'm not bragging that I got good scores on these tests. It's just a fact. But it'd be a stupid thing to brag about because I haven't had to take a standardized test in 20 years, 25 years. So why does it matter? All it does is measure how good you are at taking standardized tests. That's all it measures. I shouldn't say that's all it does. That's all those kinds of tests measure. What they do is stress people out to a ridiculous degree. So I consider things like applying tests to children, like people under the age of 18, I consider that to be child abuse. So when a school is like, oh, you have to take the SAT, I look at that institution and say, this is an abusive institution. And anytime that institution says, well, we care about our students, I say, no, you really don't. Because you're applying abusive techniques to them. You're applying punishments for no reason. You're not encouraging people to learn. You're supporting an abusive business because there's a company that runs these tests. You know what I mean? Some of you are going to have to take these tests and they're going to say there's a penalty for guessing. There's no penalty for guessing. There's a penalty for getting things wrong. But if there are 5 choices, if you have one of 5 choices on a multiple choice, the penalty for getting it wrong is 1/4 of a point. So if you can eliminate one of the possible choices, if you can take that from 5 to 4, the odds are now in your favor. You're risking a quarter point, but you're choosing 1 out of 4. So the reason that it's a quarter point penalty is that on 5 questions, if you get 1 right and 4 wrong, you have a net score of 0. So you get threatened with this penalty for guessing, which is really just a penalty for incorrect answers. Because the company that built the test does not want you to successfully guess. They're not trying to protect your score, they're trying to protect their test. Because if students get lucky and score 5 points when they guess 5 times, then their test is not really doing what they say it's going to do. They're protecting their product, they're not protecting the student. They don't care about you, they care about their product. Incidentally, that's a statement that applies to every company. They don't care about you, they care about their product. So on those problems, the quantitative comparisons, there's 4 choices. The penalty is 1/3 of a point. I'm going to continue to believe this until someone can show me otherwise. I look at this all the time, and that's the only reason I can see for these penalty for guessing. It's a penalty for incorrect answers. If you can reduce the number of choices, if you say E is definitely not the answer, now it's in your best interests to guess. Purely by chance, over the long run, if everybody just guessed, that would be a net 0 change. You might be the one that gets all the wrong answers, but that's just gambling for you. You know what I mean? I guess what I'm saying is that in this particular gamble, in my opinion, you can afford to make that bet. The payoff is too good. What if you guess right 5 times? That actually demonstrates that you're good at taking those tests. You know what I mean? So I don't see what their problem is. It's not a penalty for guessing, it's a penalty for wrong answers. So don't fall for their propaganda. Don't fall for those lies. Eliminate one of the answers, then guess. Any questions? I'm not doing SAT prep courses. I did that in college, but I was young and I needed the money. So don't judge me. I did SAT prep classes. That's when I really started to understand why the tests were the way they were. So anyway. Any questions? Comments? Snide remarks? Uh-oh, the College Board is going to come after me because I just recorded those comments. College Board is going to send the College Board cops. So what's going to happen is that like next week, once they find out next week, you're going to have like a different instructor. And so I am Professor Jones and I will be replacing Professor Leach. Or better yet, it'll be I'm Professor Smith. And I'll be like wearing a black suit with the white shirt and then the sunglasses. If he sounds like Hugo Weaving, I'll consider that a win. So if they're hauling me off to math prison for dissing the College Board, then and I'm like, oh, who's going to replace me? And they're like, oh, we got Hugo Weaving. I'm like, oh, all right, I'll go quietly, because that would just be cool. I mean, wouldn't that be awesome if Hugo Weaving was professor? I wonder how much it would cost to have him cover my classes for a semester. I'd write scripts for him. I'm not sure what his math background is. I would write scripts for him, but I mean, that would be awesome. Guest professors the whole semester. 1 week it'll be Hugo Weaving. He's going to guest professor. I'll write a script for him. He can have one of those earpieces. And so if you ask him a question, I can say what the answer is and he can just answer it. And then the next week I'll get like The Rock, because that would be awesome. Or Samuel L. Jackson. That would be excellent.
Who was it we saw?
I don't know. I always pick Dwayne The Rock Johnson.
I know, and then afterwards,
I can't remember.
damn.
That would be excellent. No one in the class is named Mr. Anderson, so it would be kind of disappointing. But anyway, that's going to do it for today. I will see y'all on tomorrow. Everybody have a good day, and thanks for playing.